give you a heads up at -15.
Good. So it's very good to see you all, including all those online who I don't see, but I know you're there. In fact, there's been all this talk about dinner and coffee and all those kinds of things. And I decided to make a personal pledge to you that even all those people who are registered online and are following this conference, I promise you that I will take you out for coffee the next time I see you in person, so, on my personal dime. Good. Well, you know, over a few years, that's okay. And I want to thank also the organizers, of course, for all the work that they've done and for setting the scene in this very nice way with the introductory comments. We really are at the dawn of a new way of doing cosmology. And while we're debating the potential and we're debating the risks, I will also not be able to hide my excitement about the subject. That's going to be the knife's edge that we will have to walk on as we go forward, and it'll be exciting. So this is a meeting on ML for astrophysics. I'm talking about cosmology, so let us first remind ourselves what we're talking about. I will focus on certain elements in my examples, mostly taken from large-scale structure surveys and the cosmic microwave background. There'll be some mention of gravitational waves. But really what we're talking about is, the ideas are really applicable to all of cosmology. And the ambition really is to scale up our ability to deal with really all of the data sets that we'll get from cosmology. And this slide is supposed to it shows you all of cosmology on one slide with a physical timeline here on the right. This is a representation of our past light cone, which is where all the photons originate that we observe, and all the gravitational waves too, all the light particles. Here's a list just of all of the observables. I think most of them, I managed to remember most of them. And this talk is really about all of that. So just to set the scene, on this past light cone, there is a special place that plays an extremely important role in cosmology. And that's this bit there at the bottom. Those are the initial conditions of the universe. If you specify that part of the past light cone, then everything else is just forward evolution. So one way to represent that, of course, this past light cone I couldn't show you in its full dimensional glory. I had to suppress some dimensions, but this disk really corresponds to a ball like this, with the idea that your world line, our world lines, to a good approximation, they're the same. All start in this in the middle of this ball, and I've colored in this ball here in this diagram with a realization of what the initial potential fluctuations in the universe looked like, or the curvature perturbations. This is an important ingredient in cosmology, the initial conditions, not just because we want to learn what happened, but also because they really tie together all of the observations. They're the common part in all of the observations that we perform later. So in the idea where we want to take all of this, everything we observe, and we want to tie it all together in a cosmological theory, we start from these initial conditions. We can then apply all of physics together with a bunch of parameters. So parameters that set the statistical properties of the initial conditions, parameters that talk about the content of the universe and its dynamics, and parameters and model components that deal with all the non-cosmological aspects of the data that we cannot avoid, which I will dump together unceremoniously in the term systematics. And and then get predictions for what the observable universe looks like. And these observations populate this light cone. They are manifold. I'm just showing you a few images here, and that's just supposed to suggest that these observations aren't necessarily easy to digest. The cosmic microwave background has treated us very well because, at least to some extent, that's an easy data set. It's very closely related to these initial conditions there. But other data sets will, and even the cosmic microwave background now, we're fully in the regime of where we're dominated by, for important problems, we're completely dominated by non-Gaussian foregrounds that are very complicated. So the cosmological inference problem just turns that arrow around. It seems very simple, but the challenge is to take all these complicated data sets that populate our past light cone and learn about all of these parameters, including the systematics and the initial conditions of the universe. And that sketches really the program, I think, for cosmology in the next decade or so, next decades even. And what do we want to learn out of all of this? I told you about parameters, but let's be a bit more specific, a little less cryptic. We want to know how the universe began, how structure was formed in the very early universe, so the initial conditions, how those structures grew, which is a function of the cosmic content, so the things that make up the universe, neutrinos, baryons, dark matter, all the components of the universe. And we want to learn how the universe then evolved and the dynamics of the universe, both in terms of growth of structure, but also globally, the background dynamics, because the expansion geometry of the universe is an important clue as to what is going to happen, which is deeply tied into the question of what is dark energy. Why is the universe accelerating its expansion today? And again, this is not supposed to be an exhaustive slide, and you can't complain that your favorite survey is not on the slide, because it is on the slide. But this is just supposed to indicate that we are populating this past light cone exponentially quickly. That can be made formal. You can look at the number of pixels or the number of galaxies, and it is actually growing exponentially. I checked. Very soon, or maybe even already today, in certain aspects of what we're doing, what we know about these parameters, about the fundamental properties of the universe, will no longer be limited by the amount of data available, but by our ability to analyze it, to use it, to interpret it. Okay, so the bottleneck for cosmological knowledge will, to a lesser and lesser extent, be the availability of data. Okay. And this is the challenge that we're facing. Okay. So why do we want, so where does machine learning come into this? I haven't even said anything about machine learning yet. Well, we have certain desires in wanting to understand, that's what I expressed here. I've sketched the situation, I've sketched the canvas, and there are a lot of things that we don't know how to do yet to realize this program. We want to be information optimal when we extract information cosmology from data. We want to go beyond certain approximations that necessity has forced upon us in the way that we do cosmology. We want to deal with these large, complex data sets. So there's a certain computational performance aspect. Generally, just we want to do things that we cannot otherwise do. And so machine learning cosmology, I think, therefore, we will not be able to avoid it, simply because experience has already shown that it enables us to do certain things that we cannot otherwise do. Now, we've already mentioned the risks involved, or the questions, the potential, but also the other side, the dark side. We are scientists, we're physicists, we're astronomers. We care about certain things that are certain principles that are part of that have become part of who we are as in our professional lives as people. detailed uncertainty quantification is extremely important and is still an open question for many of the techniques in machine learning. How do we know that we can trust the results? How reliable are the results that we get when we apply machine learning to solve some of these problems that we don't know how to solve otherwise? And can we use machine learning to really gain what we conventionally think of as understanding? And defining what we mean by understanding is a challenge that we will also have to face, and I think that we'll be discussing throughout this week. And I hope that I will be able to give you at least one example of a case where, even though maybe we don't know how the machine is doing what it's doing, the fact that it is doing it is helping us understand something. That could be a way of gaining understanding using machine learning, even though you don't really understand it sort of at the microscopic detail. Okay, so let's take a step back, having set the scene, and think about how to do cosmology in theory. One of my postdocs has taught me that in theory and practice are the same. So let's start with what we would do in theory. You write down your full physical and stochastic model of the data. You have some data. Take data first. Okay, sorry, that's point 0. Then you write down your full stochastic and physical model of the data, given some set of parameters of your model. You have to also come up with a model. Okay. Get data is number 2. Step 0 was come up with a model. Then specify a prior on the parameters of this model. The way you get the data and the way you model the data will decide what this likelihood is. That's shown there in green. Then you use Bayes' theorem to write down an expression for the posterior PDF. And that tells you what you now know about your parameters, given that you've taken that data. Okay, so you then explore that probability density function, PDF. I'll say PDF a lot, probability density function. Because that now represents the updated knowledge based on this data set that you've analyzed, or that you're analyzing. So this is actually, by the way, this is already machine learning, right? I mean, that part of maybe what's attractive about Bayesian statistics is that it's so explicitly about how to represent and analyze information, and therefore it's a language that I'll use a lot when I talk about this, because it's very adequate in this context. It's very adapted to this context. Okay, and then you're done. All right, so what's the problem? Okay, what's actually done in practice is different. In practice, what people do is that when they've taken some data, is they don't write a full physical and stochastic model of every single photon, but they pick summaries. They includes me. Okay, you pick the power spectrum. You pick the bispectrum or some other summary, whatever you think might be an informative summary and that you can hope to understand. So that second part, hoping to understand it, then leads us to point 2. You want to compute predictions for these summaries using theory of some kind. And then in order to write down that equation that I had on the previous slide, you also then have to approximate your likelihood somehow, because even though you know that things aren't particularly Gaussian, really the Gaussian is often the only practical thing that you can write down. Because if you can model the sort of the location of something and the spread, then Gaussians are a practical way of capturing that. But often there's much more going on in the tails. So that's what practical cosmology pretty much looks like. So you could call this the Peebles program, which has really been a blueprint for cosmology that was set out over 40 years ago. Yeah, this book appeared in 1980, which says use perturbation theory or some non-perturbative modeling or computational modeling, numerical modeling, to do the theory computation. It talks about the descriptive statistics that everybody is still using. These summaries that I'll call these, what Peebles calls descriptive statistics, I'll call summaries. And that's the angular and spatial endpoint functions. amongst others. Not giving a review of this book, but these endpoint functions are computed either in direct space or Fourier space, some kind of Fourier space, spherical harmonic space. So there's certain risks in maintaining this current practice. How do we know that these chosen summaries contain all of the information? Some particular endpoint correlation function may contain some sort of information, but how do we know that we've reached the end of the information that's in the data? How do we know that our theory is adequate? Right? We talked about perturbation theory. That's very good in certain regimes, not good in other regimes. So the nonlinear regime, what about complicated astrophysical and hydrodynamical processes? What about the nonlinear systematics or the difficult modeling of astrophysical foregrounds? What about the instrument model? Right? The instruments are complicated, they're sophisticated, they produce all kinds of noise and distort your data in various ways. How do we deal with that? And what about inadequate statistical approximations? So if every time you are called upon to define a likelihood, your instinct is to reach for a multivariate Gaussian, you're likely to eventually run into a situation where the tails matter. And that is always the case when you're talking about tensions. Every discussion about tensions is about the tails of your likelihood approximation. And so how do we deal with this? Well, let's start with the first one. Let's start with the summaries. How do we deal with the fact that we don't know whether the summaries exhaust information? One way to eliminate that particular risk is not to summarize. I mean, you always summarize at some level, but to summarize in a much more fine-grained way. So, for example, you can analyze the full field, analyze the entire survey, every single galaxy position in the survey, not just some 2-point, 3-point correlation function. If this is done carefully, whichever way you think about that, I challenge you to think about that in some other way, but whenever I think about this, it invariably leads to the problem of becoming entangled with the problem of reconstructing the initial conditions. Because the initial conditions set the phases. They tell you where things will end up. So if you start really trying to model the entire survey, whatever the survey may be, you have to deal with this problem of reconstructing the initial conditions or making that part of your inference problem. Well, I talked about the Peebles program, but Jim also thought of this. The notion of reconstruction and the quest for initial conditions. I don't know if he started it, but certainly was one of the first people. This is a paper in 1989, where he talks about a numerical way of reproducing the history, the assembly history of a part of the universe. Reconstructing the initial conditions generate initial conditions at high redshift. From observations. This is still a fruitful and active area, actually doing pretty much exactly, at least the mathematical background is exactly the same. So I'm giving some references here. This is a review talk. Since 2001, several people in this audience, and notably Roy Mohayai and many collaborators, have connected these kinds of approaches to questions related to optimal transport and the Monge-Ampère-Kantorowicz problem, which incidentally is also a big topic in machine learning today. So it's sort of interesting connections. So this is one nonlinear way of doing the initial conditions. There are others. The group in Berkeley with Urosh have been thinking about optimization approaches for simulating nonlinear density to reconstruct initial conditions from simulated nonlinear density fields. Chirag, Modi, and others have very recently looked at, again, using machine learning to find very good high-quality point estimates of initial conditions. Kitaura and collaborators have thought about approaches that are analogous to what I'm going to be talking about next, And Thorsten, who's in the audience, has been thinking about, let's say, a mathematical approach for deriving estimators that can be applied to nonlinear situations. And that is called information field theory. So there's a whole barrage of different things one could do to try to reconstruct initial conditions. Also related to Thorsten, to students, Jens is in the audience. We've been thinking about a physical and field-based approach to large-scale structure in this way, but rather than thinking about this as a reconstruction problem, we thought about this as a forward modeling problem. So we write down this, the arrow in the forward direction and set ourselves the ambitious goal to write down an explicit likelihood for a full galaxy survey in terms of the initial conditions and the cosmological parameters. And this sort of initial condition reconstruction using an explicit likelihood with a physical probabilistic forward model of galaxy surveys is what we call Borg. Some references there. Bayesian origin reconstruction from galaxies. So there you start from a physically motivated prior of the initial conditions, the full 3D field, that ball basically that I showed you there. Add gravity, so nonlinear gravity, and then a likelihood that says how galaxies trace this nonlinearly evolved initial condition. And a lot of other things that have to do with what happens when you observe that. So the selection function of a survey, the mask, the fact that you have bias, and so there's quite a rich model. Then you start a Markov chain over that set of parameters where every single density voxel becomes a parameter. So you have over 10 to the 7 parameters, and you do uncertainty quantification for this explicitly specified likelihood for a non-Gaussian, non-linear inference problem, data set. So schematically, observations go in, and Borg generates histories that are consistent with obtaining that data. So it gives you a measure over initial conditions and full physical histories of how structure is assembled at low redshifts, constrained by the data set, by the survey that you put in. So here's a movie that I'm sure you've seen at this point, which shows that uncertainty quantification. So here are the observations, bunch of galaxies. There's a slice through a 3D volume. Here are the reconstructions, the endpoints of those forward evolutions. And you see they fluctuate a lot where there's no data, and they're quite stable where there is data. And here are the corresponding initial conditions. And so the frames in this movie really trace out a sample of a very high dimensional probability distribution that quantifies the uncertainty in the initial conditions given this model and the particular survey that we're using here. This was Sloan. If you want to learn more about this, there's a lot more information at this website. So one thing that comes out of this, because you have the full dynamical assembly history, you can look at things like how did the Sloan Great Wall form, things like that. You have velocity reconstructions. You can use these to then apply them to other fields, debias, measurements of distances, and so forth. So is that it? Are we done? Does Borg solve all the problems? No. What we've discovered doing this, the hard way, is that the full statistical power, even of current data, is enormous. If you make a slight mistake in specifying your model, things go awry. So model misspecification is key, and that will continue to be a theme for the rest of this talk. So coming back to risks of current practice. Model risk. This is what I called inadequate theory here. This is about how do we model the data forward. Machine learning can help us there too, and Paco is going to talk about this on Thursday when he talks about simulations and numerical modeling. But But at the level of instruments, systematics, imaging, Elisabeth is going to talk about machine learning for imaging tomorrow. So this connects to many parts of this conference. But let's talk about this model risk. How do we deal with the fact that we will always be in a situation where our model isn't perfect? We have to have ways of adding more realism to our models. An n-body simulation is not a good model for your survey. So there have to be, your whole analysis framework has to be extensible, has to have the ability to adapt to more realistic modeling. The other part is kind of the negative of that. You have to have the ability to cut your data in creative ways, because you will never have a perfect forward physical model. The first line here only takes you so far. So once you start cutting the data, especially if you do it after you've looked at it, which is what everybody does. Okay, everybody does it. Will make your likelihoods non-Gaussian, for example. Right? So how do you track that? How do you keep that in your problem? How do you how do you make it easy to take out things that you know you can't model, but that don't require you to throw away the entire data set? Because there will be things in there that you can model. So this is an important aspect. And then even once you've done that, there will probably still be some aspect of the data that you haven't fully modeled, even after you've cut it, projected it, masked it in some way, in whatever space you think is necessary. And there will still be residual model errors. So to make your analysis robust, you then need to somehow model that. So here's an example of that. It's something that we call neurophysical engines. So this is a neural layer, so it's a machine learning layer that has an extremely highly constrained architecture, meaning that leads to this neural network only having 17 parameters, okay? Not 17 million, 17 parameters. It encodes certain symmetries that we think are a part of the problem. And once you put it, for example, into this Borg framework, its job is to translate the nonlinearly evolved dark matter, where we have a physical model that's tied down. It's just, we have a Hamiltonian for that, to whatever it is that you observe. And the example I show you, that was a simulation example where we assign halos based on some underlying dark matter distribution, and the network has to figure out how the halos relate to the underlying smooth dark matter distribution. The interesting thing is that in this particular case, the number of parameters is so small that you can actually learn your parameters from your data as you're doing the entire inference problem. So you don't need training data. This is how you get out of the problem of just having to make your simulations more complicated. You introduce degrees of freedom that absorb things that are difficult to model. And I should mention that there's actually, I think, philosophically very analogous approach, but based on a Lagrangian procedure, where instead of doing an Eulerian transformation of a field, instead you move the positions of particles in a way that is learned, but using very similar ideas in terms of symmetries, very small number of parameters, okay, by Selyak in this group. And so here's an example of that happening. So this is from this paper, Charnock et al., where this is Borg running, reconstructing initial conditions. Doesn't look like much yet. Here's here the set of halos in 3D. And what's going on is you have the physical forward model, and then you have a neural network this neurophysical engine that transforms this to this, which is a prediction for the number of halos that should be in any one voxel. And you see that as things are evolving, as you're sampling the network parameters, it's a truly Bayesian network. We're actually doing a sample of the parameters, the weights and biases of the network. And you have the forward model constrained by actual physics. It turns out you can solve for both, and you get at the end of this something here in the fit that is very similar to what's actually in the simulated data. Okay, so this is working. Up here you see the parameters basically predicted by the network for the halo mass distribution functions in a given pixel, conditional on the dark matter density in that pixel. And neighboring pixels, of course. Okay. So that's just an example of techniques like this, or the Lagrangian version of it, that you might use to absorb residual model errors. So now let's talk about statistical approximations. And there I should refer to Gilles' talk on Wednesday. He's going to go into much more detail, I'm sure. So remember how we did science in theory? Well, what if the data are complicated and we don't even know how to write down the likelihood? Right? That's the situation that we find ourselves in. We don't want to just assume a Gaussian for whatever summaries that we chose. But so what do we do? What do we do now? What do we do now? Okay. So now we need to go to the full problem. We have to have more freedom than a traditional likelihood approach can provide. What we want is freedom to make our physical model anything we want, so add realism, not limited by somehow the constraints of feasibility in the problem. We want the freedom to implement these complicated masks. Okay, so this is related to the second point. But then we want to actually have the ability to model the problem, including all of the complexities that this implies for your likelihood. And the key realization here is that simulating data is often much easier than writing down the accurate likelihood for it. Right? If you can just change a line in your code to change the way that a galaxy appears in a particular place in your simulation, that's much, much easier than actually working out how that changes the likelihood for the data, okay, if you really want to work at that level. And the question then becomes, so the ultimate goal would be, can we analyze data if all we can do is simulate it? Okay. So this is called simulation-based inference. It's one of the names for this. It's a name for a class of techniques for building inference engines when the explicit likelihood form is either unknown or not feasible, intractable. But simulation may be possible. So there's a great review, including Gilles, Karl Kramer, Johan Bremer, that talks about these various techniques in this class. And in fact, early uses in cosmology started maybe 6 years ago, roughly, on the image analysis side, so luminosity functions, but also on the weak lensing side, including in Paris with Martin, who did some of the pioneering work in this. But with some limitations that developments in the last few years have been able to overcome. So how does this work? How can you analyze data just by being able to simulate it forward? Well, here's Bayes' theorem again. And remember, this thing is probably very hard to calculate or even write down. But just realize that simulations just draw from this probability density function. So if you can simulate, you can draw from the likelihood, and that implicitly characterizes the likelihood. So the way this will work is, let's say you draw some parameters from your prior, you simulate forward, you get the full detailed set of your forward simulation. You then, that's your simulated data, you extract something from that simulation, and then you just check whether the simulated data are exactly equal to the true data or not. And whenever that is true, you retain the parameter that you used to draw the simulation, because that's clearly a possible parameter. And if it's not, then you don't. And you throw it away and you start again. Now, you can imagine that if I have any more than one number here, that exact equality is going to be very difficult to achieve. And even with one number, it's not that trivial often. So often what you do is you relax the criteria and you say, well, if some distance between the simulated data and the true data is less than some parameter epsilon, then I retain my simulated draw. And in the limit of epsilon going to 0, this generates parameter draws from your posterior PDF without ever having evaluated the likelihood. Okay, so this seems super infeasible because if you have 1 billion galaxies, this would basically mean, if you did this the brute force way, that you'd have to simulate forward, run a gazillion m-body simulations until all of the galaxies end up just in the same place that you happen to see them in your. And so that's obviously not feasible. So there's a key aspect of this, which is you have to reduce this data space. And that's where compression ideas come in. So imagine now, okay, you have your parameters, you simulate a very high dimensional data set. Let's say you extract from that however many summary statistics that you want, including everything you can think of, but that's still too high dimensional. It turns out you can always compress down to just n parameter compressed statistics that maintain all of the information. And this is basically score compression or moped, which I'll discuss in a minute. And then the procedure is the following. If you can do this kind of compression, you take your data, you compress your data into your data summaries, and then you basically run this program that I just sketched before. You start with, you draw your parameters from your prior, draw the data by simulating. So you have your simulated data. You compress those exactly the same way as you compress the data. So you get your simulation summaries. And then in the low dimensional space, you then compare them somehow, and that produces your posterior. So in the example I showed you before, you compare them by defining a distance, and then you accept these parameters when the distance is less than some epsilon. But there are other ways. This is still, so basically now the question is, well, how do we do this? How do we do this comparison? How do we actually construct the posterior out of these forward simulations and the data? This is described in these papers, but here are more references. Basically, one way to think about this is that you just use machine learning again to learn the probability distributions of your compressed data given the parameters. Using, for example, mixture densities or some neurodensity estimator, for example, normalizing flows. So there's the sort of frequentist version of this is that you learn the likelihood ratio, which you can then use to estimate the maximum likelihood estimator, for example. So there's been work on this for quite a while now, including by Gilles, Kyle, and collaborator. And so this idea of density estimation and conditional density estimation has really been developed by Papa Macarius and Ian Murray, and picked up, I think, in Cosmology this time by us. And so we also wrote a general package that you can use to implement this. So here's an example that shows, this is particularly a supernova inference example. This is a case where you can do the explicit likelihood approach. And this is, you run a Markov chain with hundreds of thousands of of steps. Or you just run 1,000 forward simulations of your data and use this. And it turns out it's actually faster than the explicit likelihood approach for this particular example, much faster. And you see that it gives you the right results. So just as a test. It turns out when your number of parameters gets larger, this gets harder. So often you have nuisance parameters when you're doing actual data analysis, things about your instrument you don't understand, your systematics. It turns out you can project out these nuisance parameters, the dependence on the nuisance parameters, and this allows actually extending this to many more parameters. So this is very useful. And if you want to play with this, this paper here describes the package and how to use it and all the technology that went into this, including the normalizing flows and so forth. So we talked about these summaries. So what do I mean when I say optimal summaries? I talked about wanting to be information optimal. Well, one definition would be to say that you want to saturate the Cramer-Rao inequality or the information inequality. Then if you do that, you know that there's no unbiased estimator that has smaller variance in an asymptotic sense. So this is easy if the likelihood are known. So if you've heard of moped by Allen and Raoul and Offer, a long time ago, they actually derived this doing explicit optimization of the Fisher information for a Gaussian likelihood form. But it turns out this is a particular case of what's called a score compression, which generalizes this to all likelihood forms. So that means you can take, and if you have a likelihood, you can always compress down your data into n parameter numbers that contain all of the information. But now comes the question, we've talked about situations where the likelihood is unknown or intractable. So what do you do then? Well, again, machine learning comes to the rescue. It turns out you can generalize this and ask a neural network to produce these perfect these information optimal summaries for you, even if you don't know what the likelihood looks like. Okay. So let me show you an example. And so here we'd basically be doing field-based, sort of simulation-based inference or implicit likelihood inference with these networks. So what are these networks? So just a schematic, you stick in a field, you run a neural network forwards, that's kind of a funnel shape. Architecture comes out with a set of summaries, n summaries, and you compute basically the covariance of those, and you compute the expectation, the derivative of the expectation of those summaries, and you can use that to construct a simple Fisher information matrix. And it turns out by maximizing the Fisher information in that, so this information objective here, it turns out you actually are able to compute the optimal estimators for the unknown likelihood of this data, input data. It's a little bit magical, but it does work. So the idea is that you find these optimal summaries, and the thing is this loss actually is the information, so it has physical meaning. Here's what happens for a case where we can do it both ways. Gaussian field with correlations, so we stick in this field and find parameters for the power spectrum of this field. So that works very well. It's a recent paper. You can see as you train, the network discovers more and more information and asymptotes towards the theoretical bound that we happen to know for this case. And then you can apply it to non-Gaussian situations. So this is a non-Gaussian model for cosmological density field, a log normal model. And this is just 4 different realizations. And basically training the network once, you get these optimal information summaries, and you can then use Delphi, for example, to generate these posterior contours. And the dots on top of that are kind of an explicit brute force implementation of the scheme I just told you with this accept reject. And so if you want to play with this and see how this works in practice, you can just go to this website, and there's a Google Colab notebook where you can just basically do this from any computer with an internet connection. All right, so there are other ways of summarizing the information. I talked about these information maximizing neural networks, but you can also, for example, just train neural networks based on a training set that's drawn from some prior distribution and ask the network to minimize the square distance to the true parameters. I would call those regression networks. And just one example in the context of 21 centimeter, just to show that we're not just doing galaxies or CMB. Here's the epoch of reionization light cone from a simulation. And when you then run your neural network to guess the parameters, you can use those parameter guesses as summaries and then use that to quantify the uncertainties in terms of the posterior distribution. So in this case, we don't know what the true answer is. The blue contours is what we get. But importantly, if you do a Gaussian approximation to the power spectrum likelihood, you get the wrong uncertainties. So this is an important point. So sometimes going through, basically we're doing a lot of work here in order to get the right uncertainties, and we're using machine learning to be conservative in this particular case. Because you can also underestimate your error bars and your contours if you're using endpoint functions. Okay, so all this compression stuff I just talked about sounds complicated. Can we go from the data straight to the answer? Wouldn't that be nice? You stick in the data set and it comes out directly with your parameter estimates and uncertainties. Yes, you can, but then you lose some of this safety that we had before. Before, basically, because we had these two arms in this likelihood-free inference process, if the compression was wrong, it was wrong both on your data and on your simulations in the same way. And so the worst thing that could happen was that your contours would be too wide. But you would never get, the worst thing basically is you don't get any information and you come out with your prior. You didn't learn anything. If we decide to be a bit more trusting, trust the machine a bit more, it turns out you can write down losses that, for example, basically write down sort of an optimization approach for Bayesian inference that match the posterior moments. So you can write down a loss that will, the standard actually regression loss gives you a posterior mean if you select your training set in the right way. And you can write down an analogous loss, a quartic loss, so that your network computes the variances for your parameters. Or you can write things so that instead of giving you the 10-dimensional posterior, you just directly compute the marginal posteriors in 1 or 2 dimensions, low-dimensional marginals. Turns out you can write down such losses as well. So the interesting thing is that by matching marginals of the posterior, low-dimensional marginals, you can now analyze with many parameters because you're never asking the machine to give you like the 100,000 dimensional posterior distribution, but you just look at the posterior for marginals directly. Let me skip this example. This is from a gravitational wave example with roughly 100 parameters. Here's a more interesting example with 100,000 parameters with a foreground obscured CMB data simulation. So here's your foreground obscured data. Here's the reconstruction. Let's see, and the interesting thing is here are the variances. And note that if you were doing this using, for example, Wiener filter or other techniques, you would get the variances constant across. But actually here the variances track where the foregrounds are large. Here's another example that was just submitted together with Niall Jeffrey and the group at École Normale, where we apply this to polarization. So we have a B mode, very, very small B mode signal that gets contaminated with realistic foreground simulations that are much larger. You basically pre-train the network. It's amortized, so you train it once. You can run it. You can then use it for any data set. And it gives you this reconstruction, which is very similar to the input. Where the foregrounds are large, it tends to drive you towards the prior, which is 0, which is also exactly what should happen. And the variances also track where the foregrounds are large. So it's sort of, and this is just using a single frequency. So this is, doesn't use any foreground frequency information, just the morphology of the foregrounds compared to the CMB, including non-Gaussian aspects. And this works, so if you can test, basically, given that these are simulations, we know the truth, we know the true value in every pixel, and then we can check that these posteriors actually give us the right uncertainty quantification. And for 4 different realizations here, it turns out that that works very well. Okay, so on uncertainty quantification, which is an important piece of this, here you actually get you basically train the network to give you the answer that you would have gotten if you did a hierarchical model with a Bayesian, sort of Bayesian approach. Other approaches to uncertainty quantification have certainly been discussed, but they typically focus on the uncertainties due to the learning process of the neural network. So for example, keeping in the context of foreground removal, there are Bayesian neural nets, so-called Bayesian neural nets, that train the network and then kind of perturb the weights in some way to give you a scatter on the output. And in certain limits, this can be interpreted as a posterior, but certainly it needs to be calibrated for that to be the case. Or in the 21 centimeter context, this paper trains an ensemble of networks. So many networks, they all give different answers, and then you look at how the scatter. But again, that's not really the scatter that you would have gotten if you'd done a Bayesian analysis. It's a scatter due to the the training and the network training. So capturing model error is an area of active research. So for example, integrating over architectures of the model. Okay, so now in the last few minutes, I want to look at pushing this even further. So looking at what if we could actually simulate all the way to the galaxies and all the way to images. So the Camels Collaboration is a project to generate large suites of full cosmological hydrosimulations as a function of cosmological parameters and astrophysics parameters. And these will become publicly available, and the idea is to try out these techniques on those simulations. So here are a few of them. 13 fields are extracted from 3D simulations, illustrious TNG and SIMBA, for different cosmological parameters. And I'll show you on the next slide what these fields mean. If you want to check this out, here's a website you can go to, use the corresponding paper. So these are all the physical quantities that we compute that we look at. So this is a data set with 15,000 images from these 1,000 simulations with 100 kiloparsec resolution. So this is very small scales for cosmology. And the idea is that once we release this, we really think this could be a reference data set for trying out these techniques, sort of a bit like an MNIST for cosmology. Here's what happens when you apply these moment networks. This is the moment network loss for learning the posterior mean and posterior variances for the parameters. This is using gas temperature. So the network basically predicts omega matter, sigma 8 from the gas temperature. And it turns out AGN feedback doesn't seem to be that important for the gas temperature. Here is what you learn from gas metallicity. Turns out you can estimate cosmology from the gas metallicity distribution. There are some, and this is the slide that I announced in the beginning, where I said maybe we can gain understanding even if we don't actually understand everything like at the microscopic level. One thing we find here is that there is cosmological information on very small scales. If we actually try to smooth out small scales, we lose information. So the error bars get larger. So this is what our AI tells us. Even though, in spite of all the nonlinearities, there is still cosmological information on small scales. These hydro outputs actually contain more information than the dark matter density. This may be surprising. If you because we have the dark matter, and we run this on the dark matter alone, and then we run this on all the hydro outputs, they're not necessarily directly observable. It's just a question of principle. Like if we look at the hydro outputs, can we guess back? They are in principle observable, but they will be very difficult to observe. Okay, like stellar mass, for example, things like that, gas temperature, gas metallicity, these things. It turns out you actually get better constraints on the cosmological parameters than if you give it the pure dark matter. So there is a lot of information in the hydro outputs. And maybe the most surprising result, but comforting for people doing weak lensing, is that we have these two codes, illustrious TNG and SIMBA. And it turns out if you learn cosmological parameters from the total matter, okay, dark matter plus stellar mass plus gas mass, the inferences are robust to the implementation of baryonic physics. And lest you think that this is because these implementations are very similar and these simulations look the same. I'll show you that in a minute. But here you see, this is a network trained on SIMBA and tested on illustrious. And you see that it does well in terms of reproducing the truth. This is, the line would be perfect. Here's the opposite. Trained on illustrious, tested on SIMBA. This is the green, and you see it does very well in reproducing the truth, including the error bars. So unless you think that this is because the simulations are so similar, here's a picture of the gas temperature for the same initial conditions in illustrious and SIMBA. But this clearly does not seem to matter that much to the total mass. Okay, so again, this doesn't prove anything, but it certainly is comforting because weak lensing, after all, is, probes that. Okay, so I'm not going to talk about simulation, how to use ML to do simulations, because we have Paco's talk about this. There are many interesting things here that I'm not going to talk about. But one thing I did want to mention before I close, which is that Nicolas Chartier, who's a graduate student here, has been working on this technique for that you can use to do to build in AI safety, even if you're using kind of risky machine learning techniques. Okay, so imagine that you have a way of sorry, where am I? Here. I think the battery just. Oh no, here we go. Imagine that you have a way of producing fast surrogates. So you have, for example, as people have done, Shirley Ho and not many others have generated fast n-body simulations using neural networks. Now, of course, how do you trust those? They could have some subtle effects that screw up your statistics. Okay, but it turns out that by just pairing these fast surrogates with a small number of actual simulations, you can construct estimators for any of the statistics that explicitly zero out any AI bias. So you make your AI predictions safe. So here's an example of 500 gadget simulations being used to compute the power spectrum. And here's an example with just 5 gadget simulations. The error bars are real. The blue error bars here are from 5 gadget simulations plus a whole bunch of surrogates. In this case, we didn't actually use neural surrogates, but the math are exactly the same. So in fact, neural surrogates would work better because they're more correlated. So that means you can use ML emulation or acceleration. For the cost of just a small number of actual simulations, you can get rid of any bias. This also works for covariance matrices and inverses. So watch this space. I leave this here for people who want to go through the slides later. It kind of gives you interesting ways of kind of perturbing around models and moving to new models, sort of bootstrapping from a bunch of simulations you already have to maybe a better model without having to run a lot more simulations. So my final thoughts. I hope this has convinced you that ML will help us solve cosmological problems that are currently intractable. But with great power comes great responsibility, and you've heard me mention AI safety, questions about model risk, and so forth throughout the talk. Let's use it for good. And if you really care about machine learning that doesn't involve neural computational models, then you are right. And a lot of the examples I mentioned here use deep learning, but machine learning is not equal to deep learning. And so many interesting things can be done with Gaussian processes, fast endpoint function estimators, trees, and all those areas. There's been a lot of progress, but I didn't have more time to talk about this. Information field theory, many ways of doing machine learning in this context. Okay, and then the last slide is if you find this exciting, there's some jobs here. So
Thank you very much, Ben. Okay, so let's just start with questions from the audience. So there should be 2 students with micros. So
should I take out my mask, or it's okay?
Well, if you want to, yeah. There's nobody near to you.
Anyway, thank you, Ben, for the review. Very nice. I had a question regarding your last point about using hydrodynamics constraint cosmology, which I think is not surprising. There's some information there. However, you are clearly increasing the simulation uncertainty, right, in your simulation-based inference, because the hydro simulation, the hydrophysics is much less well constrained than the n-body dark matter. Right. So how do you integrate this in your error budget, and what's the risk of doing that?
Right. So this is why we have 2 codes that have 2 completely different, 2 very different implementations. In fact, we're adding a 3rd one now, Ramses. And so, to some extent, the difference in the implementation of the different hydrodynamics is a proxy for model risk. Of course, it's not conclusive. I spent a lot of the time that I then didn't have in the end talking about ways of making your machine learning robust. So that will, in the end, that will always be necessary, and you will have to project, and you probably won't be able to use every last bit of your data. But we're at the beginning here, and we're asking these questions of principle, really. Like, what for the implementations that we have for these, very expensive and sophisticated hydro simulations, how do the outputs relate to cosmological information?
Speak into the microphone.
So these simulations fail to reproduce many of the observed hydrophysics, right? So baryonic physics. So if they don't reproduce the real universe, how do you use this to? Anyway, it's an open question.
Francois has a question.
That's consistent with what I said, I think.
Yeah, I was also picking up on the sort of same general thing, saying that we can have inferences which are robust to baryonic physics. But you were careful to sort of say total matter. Isn't it just saying that all of these codes are essentially conserving mass, and that's essentially trivial?
Oh, but this
is, of course, the code redistribute mass in different ways,
right,
and they have very different images.
Mm-hmm.
But in the end, I hope that they do conserve mass.
Right, but what I'm talking about is, so these are slices through through hydro simulations. And so I'm talking about the total matter on that slice. So so these slices could look like this, for example. So the mass distribution is can certainly be different. What's probably going on is that the heating processes that blow out gas and so forth don't actually blow out that much mass. And so even though, so here in gas temperature, it looks the differences look very impressive, but when you look at the total mass, it's less sensitive.
And the other small thing I wanted to say is you were right to sort of say it's hard to be fighting against model misspecification, and things that come to my mind immediately sort of say, what if, for instance, dark matter and dark energy are actually linked by some unknown physics? Mm-hmm. So we have to, and in all your forward modeling, of course, you are making assumptions about the physics, about the laws, and so on. And so can you say a few words about how you can explore, because the misspecification can be in various ways. It could be gravity is not GR, or in the dark matter sector, it's not whatever. I mean, so when do you open the kind of the Pandora's box? How will you deal with this?
That question, I think, is not is extremely important, but is not specific to machine learning. I think that as scientists, we're faced with that question every day. When we choose a project, we choose what model do we consider. That's one of the first choices. Do we go to dark matter, dark energy? Very, very interesting. Nothing against those models, and there's certainly codes that can make predictions for those models. The nice thing about these techniques is that they typically translate. If you put in a new code, you don't really need to change your statistical analysis. You don't, and so so these techniques allow you to leverage. If you have a code implementation, if you can simulate, you can analyze.
Okay, we better have one more question. So that was, for people following online, that was Francois Boucher. Before that, it was Mark Huertas, and now we've got Torsten who's going to ask one more question.
Yeah, very nice talk. Can you elaborate a little bit more on the data compression which you have shown, because that will be probably a key for the big surveys we are going to use. If I understood you correctly, you were proposing or doing training a machine to produce something which correlates with the quantities you're interested in. Was this the principle you used in order to train your data compression?
That's part of it. It's not just correlation. Essentially, I mean, the constraint is that you would like. So what this does is it will leave the likelihood. So these compressed quantities will leave the likelihood unchanged in an epsilon around the place where you've trained you've trained the model. So it could be that it works well far away. You certainly capture some information if you train the network at completely the wrong place. But what you know is that if the true parameters are within some epsilon of the place where you train the network, the likelihood will be exactly the same. So in that sense, it's information optimal. I've shown you there, but I didn't have time to comment. Initially, on the plots, if you go back through the slides, there are places where we decided to train the network, deliberately train the network far away from the truth. And what you find is that the error bars get slightly larger, but then the location of the contours is in the right place, and so you can then update, retrain, and capture that remaining information.
Okay, thank you.
Thank you very much again. That was super interesting. I'm sure we could talk about it for another half an hour, but we better stop for coffee. We're going to start again at 11:20. So thank you, everyone, for the morning session.
Thank you.